In section 7.2, we are going to be verifying trigonometric identities. A trigonometric identity is something that is true for all values of the variable all of the time. So we're going to use the stuff from 7.1 to rearrange our equations so that we can turn the left-hand side into the right-hand side or the right-hand side into the left-hand side. When you are verifying trigonometric identities, you are not allowed to do stuff to both sides of the equation. For example, I cannot divide by cosine y because cosine y can sometimes be equal to 0. And if I'm dividing by 0, I get an undefined answer. So what we want to do is we want to pick the messiest side of the equation, and we want to stick with that and use our identities and turn it into the right-hand side of the equation. The other thing we're going to do is we're going to continuously look at the right-hand side of the equation and try to make sure we're always proceeding in a direction that's getting us towards our answer. If you get stuck, well, you know what your final part has to be. It has to be the right-hand side. Maybe start working backwards, but never show me work on both sides of an equation. On a test, I'm just going to look straight through your work. Well, if you get like 2 steps this way, and then 2 steps from the bottom up, and all of a sudden you get the step in the middle, I can't tell that on a test, because I'm just going to see the straight work. But never do stuff to both sides of the equation. Never work partially through one side, and then partially through the other to get them to meet in the middle. And never do same thing to both sides of an equation if you're verifying an identity. So just like the last section, the only way to explain this further is to do example problems. Your problem set that I typed up for you are odd problems out of the textbook. My example problems are going to be even problems out of the textbook, just like the last section. First one, it says secant of y times cosine of y is 1. So one of the general rules of thumb that I'm going to do is I'm just going to turn things into sines and cosines to see where I get. Well, I know that, well, actually, this one's even easier. I get a number times its reciprocal is 1. So let me write out the steps I would do. Well, secant is 1 over cosine, so I get 1 over cosine y times cosine y. Notice these cancel, and I get 1. And it matches. So, again, I need to copy the right-hand side. And once I get the left-hand side equaling the right-hand side, I am done. Okay, very simple example. In this one, I want secant of x. Okay, so let's figure out what we have here. I've got cosine of x plus sine of x tangent of x is equal to secant of x. Well, let's turn everything into fundamental trig stuff. Well, cosine of x is itself. Sine of x would be itself. And tangent of x is sine of x over cosine of x. Okay, notice here, I have a fraction that I want to add. In order to add fractions, I need to multiply by the lowest common denominator between 1 and cosine of x. Well, actually I have to find the lowest common denominator, and that would be cosine of x. So I'm going to multiply top and bottom of the first fraction by cosine x over cosine of x. Notice that that gives me cosine x times cosine x, which is cosine squared x. I get sine x times sine x, which is sine squared x, over cosine x. Automatically, you should recognize that cosine squared x plus sine squared x is equal to 1. So you have 1 over cosine x. And 1 over cosine x is, in fact, secant x. And I get secant x is equal to secant x, and I am done. What's nice about these problems is you have your answer on the right-hand side, so you know when to stop. The problems in section 7.1, there were multiple answers. The book said that. I even did a problem that there were 2 ways to get answers, and I would have ended up with different answers. this one, you know what your answer is going to be, so you always know where you're going to be able to stop. That's what's nice about this group of problems. Next one. I have cosine beta squared minus sine squared beta equals 2 cosine squared beta minus 1. So I'm going to use the Pythagorean identity. I'm going to use cosine squared plus sine squared equals 1 to turn everything on the left either into sines or cosines. What I'm going to look at is my right-hand side. My right-hand side only has cosines. So I'm going to use the Pythagorean identity that's going to turn it into cosines. So for a refresher, I know that cosine squared beta plus sine squared beta is equal to 1. Well, I want to know what this is, what negative sine squared beta is. I'm going to subtract sine squared beta. Subtract 1. This work right here, I do not need to see. You should get used to, if you see sines and cosines that are squared, automatically be able to rearrange those in your head. Secants and tangents squared, rearrange those, and cosecants and cotangents, rearrange those. So where it says negative sine squared beta, I'm going to put up this. I'm going to simplify. That plus that is 2 cosine squared beta minus 1 equals 2 cosine squared beta minus 1. And I am done. So again, you need to be comfortable using the Pythagorean identities. You need to be comfortable with recognizing, hey, am I going the right direction? Am I going to do the right substitution to get to what I need on the right-hand side? I'm going to make a pause. I'm going to work through a couple more sets of example problems, and that should get you going on the 7.2 homework. The next example is sine squared alpha minus sine to the fourth alpha is equal to cosine squared alpha minus cosine to the fourth alpha. I recognize I have a common factor here, which would be sine squared alpha, which I can pull out of both terms. So I get sine squared alpha times 1 minus sine squared alpha. And I'm not going to write the right-hand side down on any of these. I'm just going to make sure I get to the right-hand side. This I recognize is a Pythagorean identity. This is going to equal cosine squared alpha. This right here, I can use the Pythagorean identity to turn it into cosines. Again, I need to have just cosines in my answer. And sine squared alpha is 1 minus cosine squared alpha. Now distribute. That gives me cosine squared alpha minus cosine to the fourth alpha. And that is what I wanted for my final answer. So again, this is just algebraic rearrangement of my trig stuff. Next example, I've got cotangent cubed t over cosecant t is cosine t times cosecant squared t minus 1. First thing I recognize is right here is that's cotangent squared. So what I'm going to do is I'm going to break this up into cotangent times cotangent squared over, and then work with this cosecant. So I have cotangent of t times, I'm going to make that cotangent squared t over cosecant t. This cotangent squared t is this part right here. So cotangent is going to be cosine over sine. So that gives me cosine t over sine t. Cosecant is 1 over cosine. So that's going to be, that's 1 over sine. So that's going to give me sine t over 1. And this is that part right there. Cosecant squared t minus 1. Notice, multiplication problem of I can rewrite it as three separate fractions, like this. And if I were to multiply this all out, I would get back to this. My sine t's cancel. And I'm left with cosine t times cosecant squared t minus 1. Next one looks really messy, but it's really not that hard. Okay, it's going to take a lot of steps, but the algebra in it is not very difficult. It's secant to the 6th of x times secant x tangent x minus secant to the 4th of x times secant x tangent x, and they want us to get secant to the 5th times tangent cubed. The first thing that I am going to do is I am going to rewrite everything in here in terms of sines and cosines. I'm going to do all of the work, and then when I get all done, I should be able to turn things into secants and tangents. The reason why I'm turning it into sines and cosines to me is working with the fundamental trig functions is a lot easier. So secant is 1 over cosine. So I'm going to write 1 over cosine to the 6th x. That is 1 over cosine x. And tangent is sine of x over cosine of x. So that's the first part of the left-hand side. Second part is going to be 1 over cosine to the 4th of x, 1 over cosine of x, and then sine x over cosine of x. So please notice that both sides have a sign on the numerator. The denominator here is cosine to the 8th. The denominator here is cosine to the 6th. In order to add fractions, I need to have a common denominator. My common denominator is going to be cosine to the 8th. In order to get this right-hand fraction to cosine to the 8th, I need to multiply the numerator by cosine squared and the denominator by cosine squared. So, what this is going to give me is 1 times 1 times sine is sine x minus sine x cosine x over cosine to the 8th. I have a common factor in both of these, which is sine x. Pull it out, and I get 1 minus sine. Actually, that's supposed to be a cosine squared x from up here. One minus cosine squared is sine squared. Sine squared times sine is sine cubed. So I'm going to write this as sine cubed of x over cosine cubed of x times 1 over cosine the 5th of x. Please note the denominator, cosine cubed times cosine to the 5th, in fact, cosine to the 8th, times sine cubed is sine cubed. So this is valid. The reason why I did that is I want to turn it into secants and tangents. Okay? So my tangents are right here. Sine cubed over cosine cubed is tangent cubed. And 1 over cosine is secant, so that's going to give me secant to the 5th. And notice I was able to rearrange the order of the multiplication because of the commutative property of multiplication saying that order does not matter. Okay, so again, I turned them into the fundamental trig functions. I did all my little algebra. Or actually, this is not even algebra, it's arithmetic. Did the arithmetic, and then turned them back using my trig identities. Got one more group of examples, and we'll be done with 7.2. Okay, for the